Welcome to our last lesson in our series on electrochemistry. In today's lesson, we will look at two more applications of electrolysis in industry. We will first look at the electrorefining of copper. In this reaction, both electrodes are made up from the same metal. The anode is made of impure copper and the cathode is made of pure copper, and it is then placed in an acidified copper sulfate solution. Here is Simbolelo to tell us more about this process and also electroplating.
Have you ever taken the time to notice how many things in your home are made of metal or contain metal? Cutlery, food tins, door handles, the television you are watching, even the pen you are using to take notes. The interesting thing is that none of these metals are found naturally in nature. They're almost always found in compounds, and mostly these compounds are ionic salts where the metal is a cation. Many important metals such as copper, nickel, and aluminium can be found in the earth as salts. To use them, we need a way to add electrons to these ions, reducing them into metals. We are going to be joined by Legend to see how this is done.
Hey guys, nice to have you back. Today we will be revisiting an experiment you may have seen before. We will be using electrolysis to make copper metal from copper 2+ ions. You will remember that the copper ions are blue and the metal is brown, so it will be easy to see whether we produce the product we want. First, I'll make a solution of copper chloride salt and water. Then I place the two electrodes into the solution like this and turn on the power to supply potential difference to the electrodes, giving them the energy needed for the reaction to happen. Now we allow the current to flow for some time. Look carefully at what happens. Look closely at what is happening at the cathode, the electrode connected to the black wire. I am sure that you can clearly see that a new brown layer of metal has formed on the cathode. This makes sense. The positive copper metal ions are attracted to the negative electrodes. Here they gain electrons and become copper metals. This shows that metals can be made by reducing them from their salts. Let's get back to Sibu and see how this principle is applied in the industry.
Thanks, Legend. We mentioned earlier that most metals we use every day is extracted from their salts, and now we know how.
Sure. All you need is a cathode and electrolytic cell to turn ions into useful metals.
Exactly. Very large mining companies in South Africa use the very same process we saw earlier to produce metals. The process of electrolysis they use is called electrorefining. This term is used to describe the recovery of metals such as nickel and copper from solutions of their ions by using electricity. But electrolysis isn't only used by mining companies to make metals from mineral salts. We can also use this process to place a thin layer of metal over another. Often, a more expensive metal like silver, gold, or platinum is placed over a less valuable metal to make it look better. This also greatly reduces the cost of the item because a less precious metal is used to manufacture it. For example, door handles are often coated with chrome as it has a nice metallic shine and is resistant to corrosion. The inside of the handle is made of cheaper and stronger iron. Let's go back to Legend and see if we can demonstrate this idea.
Hey, glad to be back. We're going to try do some electroplating. We will be taking this electrode and hopefully coat it with a nice shiny layer of silver metal. Here are the things we will use: a copper electrode, a carbon electrode connected to a power supply, silver nitrate powder, and water. So the method we will use is exactly the same as the previous experiment. First, we make a solution of silver ions in the water. Then we connect our power supply. Remember, the negative terminal is connected to a copper rod. This will attract silver cations. Wow, look at that! We can actually see the layer of silver covering the wire.
In both experiments, we used electricity, and in both we dissolved the copper chloride and silver nitrate before the experiment. Can you think why this is necessary?
It is because the ions need to move free, right?
Absolutely right. In a solid, the ions would not be able to reach the electrodes.
We can summarize the electrorefining of the copper in 4 easy steps. A bar of impure copper that contains other metallic impurities acts as the anode. The cathode is made up of pure copper with few impurities. The electrolyte is a solution of aqueous copper sulfate that is acidified with sulfuric acid. When current passes through the cell, electrolysis takes place since it is a non-spontaneous reaction. The copper in the impure copper anode dissolves as copper 2+ ions that move through the solution to the cathode. The half reaction that takes place at the anode is solid copper that dissolves to form copper 2+ and 2 electrons. At the cathode, the copper ions precipitate as pure copper according to this half reaction. Copper 2+ and 2 electrons form solid copper atoms. The concentration of the copper 2+ solution remains constant during the reaction since the rate of oxidation is equal to the rate of reduction. Did you notice the layer that formed below the anode? These are the impurities. Some of them dissolve, while others like silver and platinum and gold form the layer at the bottom of the cell. This is a valuable byproduct. Remember I said that we will look at 2 processes in this lesson. Well, here is Simbulelo to tell us about the extraction of aluminium.
Now it is time for us to see how the metals industry manufactures metal on a very large scale. We're going to be looking at a very specific metal, aluminium. Aluminium is a metal with many great qualities. It is light, strong, and it doesn't rust. This makes it useful for many items in the home and in the workplace. These qualities also make aluminium the ideal metal for building the wings and body of aeroplanes and helicopters. Although aluminium is a very reactive metal, it forms a protective coating of aluminium oxide when it is exposed to air. This means that aluminium does not need to be painted. But it also means that it is not found as a metal in nature. It is only found as an ion in aluminium oxide. To make matters worse, aluminium oxide does not dissolve in water, and even if it did, the aluminium formed would react violently with the water. The only way to make sure that the aluminium ions can reach the cathode is to melt the aluminium oxide at 1000 degrees. Aluminium oxide is found in a mineral called bauxite. Most of the bauxite that is used in the aluminium production in South Africa and Mozambique comes from Australia. It is mined from the ground and purified to alumina, the mineral name for aluminium oxide. It is then transported to Maputo and Richards Bay on the ships for processing. Once the aluminium oxide reaches Richards Bay, it is mixed with a chemical called chrylite. The chrylite is added to lower the melting point of the aluminium oxide to 1000 degrees, making the process much easier and cheaper than it would be otherwise. Large electrical conductors carry current into the large steel containers, and this is where the electrolysis occurs to make the molten aluminium metal. The aluminium is a liquid at this temperature. It is then allowed to cool into large blocks or made flat sheets and curled up into large rolls, each weighing several tons. The really interesting thing, of course, is what's actually occurring inside the cells. Let's take a closer look. The container is lined with special heat-resistant bricks. Over this is layered a conductive layer of carbon. This carbon layer is negatively charged and plays the role of cathode. The anode is inserted at the top of the container and is positively charged. When the current is applied to the electrodes, the magic begins. The positively charged aluminium ions are attracted to the cathode at the bottom. It is reduced to aluminium metal, the substance we are after. Can you guess what is going on at the other electrode?
Well, the mineral we're dealing with is aluminium oxide. So, at the other electrode, oxide ions are being oxidized.
That's right. The negatively charged oxygen ions are attracted to the positive electrodes, where they will lose their charge. What do you think the product will be?
Oxygen,
One would think so, but actually no. At these temperatures, the oxygen combines with the carbon of the electrode, making carbon dioxide a greenhouse gas. This process of extracting aluminium is called the Hall-Heroult process. Aluminium is produced in this way on such a large scale that the hillside plant in Richards Bay consumes nearly 10% of South Africa's electricity. Interestingly, we also use electrolysis in recycling aluminium from cans, like cold drink cans. Cans are collected, crushed. We then use electrolysis to recycle the aluminium. As you can imagine, this process uses much less electricity.
Thank you, Simbulelo. We enjoyed your help during this series of electrochemistry, and we realized the importance of recycling. Let's just summarize the process of forming aluminium from bauxite again. The bauxite that imported is crushed and treated with concentrated sodium hydroxide to form pure alumina with the formula Al2O3. This aluminum is melted at a very high temperature so that an electrolysis process can occur. During the process, aluminium ions are reduced to aluminium atoms and oxide ions are oxidized to oxygen, according to this overall cell equation. This whole process requires a large amount of electrical energy, and therefore the process is extremely expensive, and it contributes to carbon dioxide greenhouse gases. This concludes the series on electrochemical cells, and as always, I refer you to the task video to practice these concepts. Remember to make use of your datasheet to help you. You'll also find more information on our website. Goodbye, Matrix, and keep well.